trickling. Hello, Nikki. Are you able to hear me?
Good morning, DV.
Hi, DV. We can hear you.
Very good morning. A warm welcome to Madam Mamta Rani Agarwal, please. Madam Mamta Rani Agarwal, please. Hello. Do we have Madam Mamta Rani Agarwal?
Hi, DV. Would you mind telling Ms. Manta to accept the panelist invitation?
Sorry, Nikki, could you please come again?
Would you mind telling her to accept the panelist invitation?
Hi,
Sure,
good
okay.
evening,
there
everyone.
we
I
go.
can
Oh,
hear
there
you
she is.
loud and clear.
Awesome.
Great,
Thank you.
thanks.
Okay, so Nikki, can I start the initial remarks?
Yes, yes.
Okay. A warm welcome to all the panelists and participants. This is Venkatagiri here on behalf of Explore the Space. This is the 5th edition of the international webinar series on future of space technology and exploration that Explore the Space is doing in association with Elcon Precision. Elcon Precision is a top-class metal finishing company and a direct supplier to NASA. Ladies and gentlemen and friends, we have a very illustrious panel today, and the webinar is going to be inaugurated by Madam Mamta Rani Agarwal, advisor of All India Council for Technical Education. Madam, most welcome to you. So we have
So can you hear me?
Madam Mamta Rani, am I audible?
I can hear you loud and clear. Can you hear me?
Okay. Yeah, I'm able to. So moving on, we have a very illustrious set of speakers, which includes Mr. Tim Dyer, the main force behind this program, and the president of Elcon Precision. And we have a very interesting and energetic speaker in Mr. Scott McCormack, who is the assistant professor of material science in University of California, Davis. Now, ladies and gentlemen, just bear with me as I'm going to take you through a very brief presentation. Nikki, I'm just going to my presentation. Nikki, can you, may I request the presentation, please?
Oh, yeah, you can share your screen at the bottom, DV, when you have it open, unless you want me to put it up.
Yeah, because I'm not able to do that.
Okay, let me do it for you.
Yeah.
Yes.
Thanks, Nikki. The next one, please. Yeah, this is the panel today. Madam Mamta Rani Agarwal, Mr. Scott McCormack, Mr. Tim Dyer, and our team consisting Professor Sumitra Devi and the science writer, Mr. Balagurunathan. Next, please. For the newcomers, for the first timers, Explore the Space is an NGO promoting space education across geographies in association with Elcon Precision, a metal finishing company based in San Jose. And we are bringing to the world audience this webinar series. We are doing this webinar series with 3 objectives: to encourage the global youth to pursue STEM education and space technology, to facilitate industry-institution linkages in space and allied industries, and to emphasize on global space cooperation. These are the 3 main objectives with which we are doing this webinar series. Next, please. Ladies and gentlemen, the first edition had Mr. Tim Dyer, the managing director of Elcon Precision. That was on 25th June, about a year back. Who spoke on advanced materials for launch vehicles. The second one had the edition 2 had Dr. Jaideep Mukherjee, Director, NASA Florida Space Grant Consortium, who spoke on NASA's Artemis mission, humanity's return to the moon. This was on 14th September. Next, please. The third edition had a very interesting panel discussion comprising Tim Rebecca and Nikki, who spoke on microsatellites, manufacturing and operating technologies and challenges. The fourth one was in February, where we had Mr. Ed Tomasic, Director of Business Development of Elcon Precision, in association with Dr. Ram Prasad Gandhiraman, founder and CEO of Space Foundry, a San Jose-based company, and they spoke on human exploration of outer space. Next, please. Friends, all the 5 editions of the webinars, including the one today, have been inaugurated by a very illustrious set of speakers, both from the international arena as well as from India. We have had Dr. T.V. Nagendra Prasad, Consul General of India, San Francisco, Madam Grace Akello, High Commissioner of Uganda, Mr. Nishroj Pon Prasarat, Consul General Thailand, Mr. Joseph Abraham, Consul Trade and Commerce, Israel, and today we have Dr. Mamta Rani Agarwal, Advisor of AICT. That's a very, very illustrious bunch. We have been very lucky to have this kind of eminent personalities to inaugurate our webinar. Next one, please. The main idea why we are running this webinar series is to encourage the youth to pursue various careers in space industry, which would range from additive manufacturing, aerospace engineering, and the list goes on. It also comprises ground systems. Next one, please. And again, why we are doing this is essentially to build a future workforce for the space industry. We would like to showcase the diverse career paths in the space sector and to space professionals working internationally. Next, please. We have been the authorized support partners for Space Tech Expo USA and Space Tech Expo Europe. We had the opportunity to be there in Long Beach about 3 weeks back, where we presented this bulletin to the exhibitors. We also encourage the audience, the industry, and the institutions to take part in Bangalore Space Expo. That's going to be from 5th to 7th of September 2022. Another 2.5 months from now, we will be participating in the Bangalore Space Expo. Next, please. We encourage the students to join the International Online Certificate course, which will be launching shortly in association with Elcon. This is for students age 14 and above from schools and colleges all over the world. Next, please. That's about the international student membership. We welcome the students across geographies to be part of this mission in promoting space education. Coming back to today's particular webinar, I would request the attention of Tim and Scott. We have had questions from close to 100 plus audience who have registered for today's webinar. Their questions are ranging from rocket launch, nanotechnology, thermal protection system, satellite, International Space Station, sensors, space observatory, and the list goes on. I'm sure today, and as this series goes further, the youth, the students will have a great learning, and that's essentially the objective of this webinar series. Next one, please. That's about it. Now, ladies and gentlemen, I have pleasure in introducing Dr. Mamta Rani Agarwal, who is going to inaugurate today's webinar. Dr. Mamta Rani Agarwal, presently working as Advisor 1 in the All India Council of Technical Education, is former Additional Secretary, Association of Indian Universities, former Joint Secretary, University Grants Commission, and Director, Education, New Delhi. He is also from the first batch of Lady Pilot Officer in Indian Air Force. Most welcome, madam. It's our pleasure, and we are honored to have your presence here. Mrs. Agarwal has been an international speaker at the School of International and Public Affairs, University of Columbia, New York, on urban education, innovations in K-12. She has represented the country in the Global Summit on Reforming School Systems in Global Cities, New York. Under her leadership, All India Council of Technical Education Training and Learning Academy, what we call as ATAL, has been recognized, conferred award, and included in the India Book of Records, Asia Book of Records, and World Book of Records for outstanding contribution in the faculty training and development. Mrs. Agarwal has been an expert member on the task force on the implementation of national education policy in AICTE. Madam, we again welcome you, and it's a pleasure to have you here. Over to Dr. Mamta Rani Agarwal for the initial opening inaugural remarks. Thank you, please.
Good evening. Am I audible?
Yes, ma'am, you are audible.
Good evening. Our theme address, Tim Dyer, President ETS-Elcon, President Precision, San Jose, California, United States. Keynote addressee, Scott Cormack, Assistant Professor, Department of Material Sciences and Engineering, University of California. And Dr. Venkatagiri, CEO, Explore the Space, the Global Trade Driver, Chennai. You know, when he approached me, when Dr. Venkatagiri approached me, I kept on telling him that I am not the fit person. Probably, you know, I am one person who hardly knows anything about space exploration. But then his persuasion finally made me give up, and today I am in front of all of you. So good evening to all the participants from India, and good morning to all my friends and fellow speakers from the United States. On behalf of All India Council for Technical Education, which is the apex national level regulatory body in India, I deem it a privilege to address this August gathering. When you speak on a digital platform or in an online platform, it is very, very difficult to connect to your audience because there is no bodily perception, there is no eye contact. You don't even know as if anyone is listening to you or not. But nonetheless, this is what it is. And let me make my attempt to speak on a very interesting webinar series, Future of Space Technology and Exploration. Today, specifically today, it's a great day for space exploration and technology in India. And all my fellow panelists and Dr. Giri would agree that today, New Space India Limited, a public sector undertaking of Government of India, and the commercial arm of Indian Space Research Organization. Like, let's say you have NASA in the United States, so we have ISRO, Indian Space Research Organization. ISRO successfully undertook the launch of GSAT-24 in its first ever demand-driven communication satellite mission. Post-space sector reforms, leasing the entire capacity on board to India's leading direct-to-home service provider, Tata Sky. So today's successful mission of GSAT-24 is a major step forward for ISRO in commercially meeting the DTH communication needs of our country, India, using indigenously built satellite solutions from ISRO. According to industry estimates, and there is a Morgan Stanley estimate, that the global space economy is pegged at $423 billion. And India will also be considerably contributing to it. Even if we consider the least contribution, it is going to be roughly 3%. Global space industry is expanding and is likely to expand to the tune of $1 trillion by 2040. As part of space reforms announced by our government and Government of India in 2020, this NSIL, which is, I told you, the commercial arm of ISRO, it has the responsibility to build, launch, own, and operate satellites and provide services to all its committed customers, either in India or globally project. As per the recent media reports, which I actually read in the newspaper, the government further plans to announce, expand many more reforms that could see the rise of India's or SpaceX-like ventures. And who in India, and I'm sure, you know, even my fellow panelists from abroad know, you know, the success of our moon mission, and you know how beautifully, with limited resources, with limited economic resources, India has done wonderfully well. Again, our upcoming solar observation mission, which is named Aditya L1, is going to be the first Indian observatory class mission to study the solar corona. our future of space technology. And when we talk about our future, I'm talking about Indian future, a country of technocrats, a country of engineers. And exploration is actually a story of human exploration, technology, science. We are probably getting ready for India's first manned mission in space called Gangayaan. See, the world is moving towards convergence. The academia is moving towards convergence, and so is our space mission, which is moving towards convergence. So let us learn from each other. We'll go to space to learn more about what it will take to support human exploration to Mars and beyond. Our technocrats are developing new technologies to meet the challenges of advanced space exploration. Our scientists will work to increase an understanding of our planet and our place in the universe. We all together will continue to try to answer the question, are we alone? Are we actually alone? We as a nation plan to build upon the community of industrial, international, and academic partnership forged for the space and will continue to be a global leader in scientific discovery, in space discoveries, fostering opportunities to turn new knowledge into things that improve life on Earth and beyond, if actually it can be. While artificial intelligence, machine learning have gained popularities in recent years, India is still in its infancy in the field of aerospace engineering education. So when people like Venkatagiri, they come forward and tries to encourage youth to explore their interests, their capabilities, their career in aerospace engineering education, I think it's a praiseworthy step. And I admire and I acknowledge the work of Dr. Giri in this. AICT is promoting technical education in artificial intelligence, machine learning, aerospace engineering, as there are wealth of opportunities due to ever-changing technological landscape. And again, one of the best part, as it is part of any mission, even with the space technology, it's a convergence of all sciences, it's a convergence of all technology, whether you talk about chemistry, or you talk about physics, or you talk about metallurgy, or you talk about biology. Not only that, even if you talk about the psychology of the people who actually go to those spacecrafts. So let all of us come together, use space, use the technology, use our satellites to make sure that we actually create a better world, a world in which all the natural calamities can be predicted well in advance, a world where we always know that, what kind of weather are we expecting, where communication can be better, where connectivity can be better, where all our intelligence systems working for the betterment of humanity, for the betterment of global community, and let's make a better world. Thank you so very much, Dr. Venkatagiri, for inviting me here. And definitely, I am not an expert in the field. So look forward to Tim, and look forward to Nikki, if at all she's speaking, and look forward to Dr. Scott from University of California to actually apprise us as to, what are we looking forward to in the space exploration. Thank you so very much, my dear friends, my dear panelists, co-panelists. Thank you for inviting me here. Thank you.
Thank you. Thank you so much, Dr. Mamta Rani Agarwal. Thank you, ma'am. Thank you for your emphasis on convergence. That was a very, very important point. Thanks for the encouragement. And explore the space in association with Elcon Precision will definitely take this mission forward of global space education. Friends, now we move on to the main program. We have a very important speaker, as I mentioned before, the main force behind this program. That's Mr. Tim Dyer. A few words about Tim Dyer, the president of the material science firm Elcon Precision. Elcon Precision is a firm that specializes in photochemical machining, metallization of ceramics, and brazed assembly services. Tim is a material scientist and a senior executive with 25 plus years experience working as process engineer, ceramist, senior engineering director, vice president operations, Chief Technology Officer and President for startup to medium-sized public and private companies with a bachelor's and master's in material science and engineering from University of California, Davis, creating and making products at nexus of energy, fabrication, technologies, and material science is a special feature of the distinguished career of Tim. Over to you, Tim. Thank you again.
Well, thank you, DV, and thank you all those who are attending. I'm very excited about engineering and science, and having Elcon components out in satellites and Starlink, and also in flying out in the NASA DART mission or ion engines. It's been a great ride, and also this is a anniversary, I guess, of these seminars. So I really appreciate all the work you put into this, DV, and your passion to get other folks interested in STM education. That's really major. So thank you very much. Today I was going to go ahead and share my screen here. Nikki, I need to be able to do that. Let me see if I can. Unless Nikki can do that for me. It puts my slides up.
Are you able to share right now? I think I.
Yeah, I did. Hold on. It says Nikki. Let me see if I could share now here. And then do you guys see my slides?
Yes. Yep.
Let me see if I can do the whole thing in it. Oh, sorry. Okay. Okay, let me see if we can do the, do you see my full slides or the?
We see the black screen, the one with the notes.
Okay, let me see if I can get this right. Display settings.
I can see his slide. I can see
there we
his
go.
slide.
That's it.
Yeah.
Okay, great. Well, thank you. Well, thank you, everybody. And it's like with these events, we're not professionals. We try. We're scientists and engineers. We're not media people. But thank you for attending. Today, I'll be talking about tungsten metal applications for solar exploration. And this was mentioned earlier that the sun is of great interest in study. So a little bit more about me, to understand that I'm a normal person. I am native of California, and I'm a German. I'm the son. My mom was German, so I'm a German immigrant with my father's U.S. and my mom's from Germany. So like a lot of people at Elcon United States, we have multiple nationalities. So Elcon has 45% female employees and has over 13 different nationalities at work. So part of Silicon Valley is when you have a group of multicultural people working together, you get really excellent results. So in the end, diversity is key to creativity and to a really successful operation. I attribute that to Elcon. I'm a material scientist. Since 1989, I got my degrees from University of California at Davis, both bachelor's and master's. And I strongly suggest that if people are interested in either graduate or undergraduate education, at UC Davis is an excellent school. And that's why I've asked Scott McCormick to help with the presentation so that we understand how important it is to get that education to stay in STEM. Also, my hobbies are mountain biking, yoga. I do that, traveling, and I make bad wine. And then when I was young, to understand my youth, is I played a symphonic orchestra for many years, and I used to work with VW Beetles, Käfers. I don't think they exist anymore, but it was a very small vehicle that the Germans made that were very easy to fix. A little bit about Elcon. It was founded in 1967 by Anthony Baracco. We have 53 people. We're AS9100, ISO, ITAR, so we work with aerospace components and also medical. We're privately owned by a group of US companies. And then this is our main motto. As a team of material scientists and fabrication experts, our mission is to apply our innovative and collaborative problem solving to pursue solutions that ensure success in critical applications that directly contribute to the preservation and betterment of human life. That's our goal as a company. So we want to make things better for everybody. That's how we succeed. Now I'll be talking about tungsten metal. And some people think tungsten's a compound. I hear this occasionally, but actually it's an element. Tungsten, it has some amazing properties. So I'll talk about tungsten. If you look at the periodic table of elements, we see that tungsten is a transition metal. It kind of lives in the middle of the table. A lot of the materials in the middle of the table have unique properties because the way their electrons are configured, they have a lot of options, I would say, chemically. They also can create colors in ceramics and in glazes for pottery. So these are great elements. Like manganese is red and chrome, I think, is green. Titanium is blue. So you see these in pigments. But today we're talking about tungsten. He's element 74. Some understanding of tungsten is what's interesting about it is it's a heavy metal, very heavy. His atomic weight of 183 grams per mole. It has a melting point of 3,410 centigrade, which is crazy hot, very unusual, and that's the highest melting temperature of any pure metal is tungsten. So that's what it's claimed to fame. Its density is almost 20 times that of water. So lead is only 10 grams per cubic centimeter, so it's twice as dense as lead. So a small piece of tungsten is very heavy material. It is also a body-centered cubic, and this is for the people who want to understand material science, is that the crystal structure of tungsten gives it some unique properties where it is very brittle like ceramic at low temperatures, and then you heat it up, it becomes ductile and pliable, just like aluminum. But it's an interesting metal that when it's cold, it behaves, it's like glass. Very, very unique material. And then some unique attributes of tungsten. Tungsten is actually a Swedish name for the mineral scheelite. So the initial work with tungsten was discovered in scheelite. The work that of main note, which is done in Germany, was a person by the name of Wolfram. So tungsten is called Wolfram in many European languages. So it actually goes by a few names. So in the United States, we call it tungsten. Europeans may call it something different. It is the highest melting point of any metal, as I explained earlier. It's also a great X-ray absorber. So if you want to block radiation, tungsten is phenomenal at doing that. And it is actually used in cancer treatment machines for cancer. They use tungsten windows to adjust the X-ray radiation beam, the shape of the beam. So it is a great absorber, very hard, heavy material, brittle. It has a dull gray appearance, and we all probably know it from light bulbs. So if you have a light bulb in your car, a halogen light bulb, or if it'd be an old-fashioned light bulb in your home, typically the filament is tungsten. So that's how we all know it. Here's some applications that Elcon uses tungsten for. We are one of the few companies in the world that actually photochemically machine and manufacture components out of tungsten. Strange claim to fame. It's used for looking at the sun for gratings that are actually looking for imaging. It is also used in knee surgery when the surgeon orthoscopically needs to cut something to put in your knee implant. Maybe your grandparents or your parents had knee surgery. It's used for a lot of the cutters in the knee surgery operations. People use it for markers in X-ray because it's X-ray, it blocks X-ray. So if you need to take an X-ray image, you could put little markers of tungsten and you take an image and you could see where it's at. So it helped to point things out. It makes windows, like variable aperture windows for cancer treatment. And it's actually used in a Varian Medical's company. They have the Halcyon, which is the most advanced cancer treatment machine made. One of the most advanced machines uses this material, and we're a proud supplier of Varian Medical. Okay, now we'll talk about the sun. We see it every day. Well, hopefully, if the weather's okay, it's really important. So I think it's good that we kind of understand more about the sun. And of course, that's a Paul McCartney thing. Here comes the sun. But anyway, for you people who like the Beatles or old enough to remember the Beatles. Some facts about the sun. It's the center of our solar system, and it's big. It's 100 times the diameter of Earth. So it's very, very big thing. Its surface temperature is 5,000 centigrade. So remember, tungsten melts at 3,400 centigrade. So this is hotter. So if you flew a tungsten component into the sun, it would melt. But it's hard to imagine how hot it is. But even what's more amazing is that the center of the sun is 15 million degrees centigrade. And that's really hot, and that's because there's a lot of I say reactions are causing fusion reactions are generating energy. So all this happening in our sun creates all the energy that supports life on Earth. So if we didn't have the sun, we wouldn't be around. So that's how important it is all the energy is created by this miraculous object, the sun, really helps us live. It is composed of very normal things. You wouldn't expect it. It's 70% helium. and it's 28% hydrogen gas. And hydrogen actually could be very important to the future of our energy in the planet too. As we run out of fuel like oil, we probably have to do hydrogen. So it's already being used to help us gain energy. It's just out in space. There's also some elements like iron and a few other things in the sun that are in there, but it's mostly helium and hydrogen. It takes 25.4 days for it to rotate at its center axis. So it is slowly spinning, kind of like the planet Earth, but it has a very long day. And it creates a lot of energy, a lot of radiation. Most of it's good, some of it not so good. And that's why we need to study it to understand what is the good and what is the bad of the energy it creates. The sun is a layered thing. So it's like kind of like pudding, like dessert pudding. Where it has some inner layers. There's a core and a radiative zone and a convection zone. So there's a lot of hot moving of gases in the center of it. And then there's some outer layers, the photosphere, chromosphere, that are kind of in the corona. And the corona are like the little wisps of energy that come off of it. And we can see these sometimes with if you have a telescope, which has a sun viewing equipment. I had one as a child. You can actually see the corona. Nowadays, we have more advanced machines that we send into space to look at the corona, and we can study it better. And again, folks, the temperatures in this slide are in Kelvin. So the Kelvin is related to centigrade. You have to add 273 to centigrade to get Kelvin. So that's why the little equation is there. Because when you talk about hot things, people tend to go into Kelvin. And no one uses Fahrenheit when it's really hot. I haven't used it in a long time. Though in the United States, we'll talk about the weather being 80 degrees Fahrenheit, but when we talk about super hot things, we use centigrade or Kelvin. So great, you can see the layers of the sun. And then the little dot in the upper right-hand corner is how big the Earth is compared to the sun. So just understand how big this thing is. Now, there's many ways, interesting things about the sun. The color of the sun is important. So if you see big red giants, they're actually colder. So a redder sun is a colder sun, maybe 3,000 degrees Kelvin on its surface. The white suns are much hotter, could be 10,000 Kelvin, and blue suns, which some exist, are really high energy. And that means they're very hot. So they may be large, but they can also be different temperatures, like the temperature of your stove. So some burners can be big and burners can be small. Some can be hot, some can be cool. And there's some examples in this diagram. You see that Rigel is a very large sun, much bigger than our sun, and is very hot. And then you see Antares, which is a red sun, which is much bigger, but it's very cold. And then our sun is located sort of in the middle of this diagram. You can see where it sits and it rests. And it's, again, saying around 5,000, 6,000 Kelvin is what the temperature of our sun is. So understand that suns are of different size and different temperatures. And that's why we want to study the space and study our sun to understand, why they're so different. So let's talk about imaging. And recently we've come into some great images of the sun and the energy of the surface. So digital photography, gratings, space satellites. These are fairly new that they've come out, and this is most of the work here is done by NASA. So we can actually see how marvelous the sun is. And this is an image of a sunspot by the Solar Explorer, which is a NASA mission of a satellite that's circulating the Earth that actually takes pictures of the sun. It's actually on its way to the sun. The reason it's pretty hot out there, so I'll explain a little bit why tungsten's involved. This is another version of a new explorer that's going to be launched called the NASA IRIS mission. It's a new camera that's being developed, and when you're out in space, there's no air to convect heat. So heat is actually convected via radiation. So it's almost like waves of energy. And as something approaches the sun, it gets very hot. So you can't have a low melting temperature metal. Just by looking at the sun as you get close, you could achieve surface temperatures exceeding 2,000 centigrade. So you need a material that would actually allows you to look at the sun like a lens, but most glasses would melt at that point. So the tungsten becomes kind of a lens that they use in these devices, these machines, to image both the sun and its radiation. They're called gratings. So here's the grating assembly for the Solar Explorer. So this is a component that is actually a grating, like we say diffraction grating. It's a series of slots, and it's made out of pure tungsten. And this is intended to image solar flares and characterize solar radiation. And this is actually a print of the device. It's about 1 inch thick. It may be 200. It's about 25 millimeters thick with about 150 millimeter diameter. So you understand how big this window is. And this is actually on the front of the camera, the imaging system of Solar Explorer. This is one that's actually made by stacking up many, many thin layers. So like a book, if you take a thick book and you press very hard, all the layers create a very solid substance. Well, it's actually put together with a high temperature and pressure called diffusion bonding, which allows you to form a very thick component of tungsten with very narrow slots in it. It'd be very impossible to do this via machining. It's only possible via diffusion bonding and photochemical etching. And Elcon, we're a proud supplier of this component. Here's actually from our trade show some real pictures of the components that were used in the grading. These are extra parts that we had. So you can actually, this is a tungsten sheet. You can see the very thin channels that have been etched into it. And this is, again, these 3 components are part of the layered stack that's going to be put together. And the holes on the outside, you see like the 2 round holes are where the pins are put when they stack them all up. So when they push on them at high pressure and temperature, it all bonds together. It all aligns perfectly. Very, very interesting component. And here are some pictures from it, so you can understand how wonderful and chaotic the surface of the sun is. The picture on the left being more of looking into the sun, and then some corona discharge photos that are out on the side. So it's really great stuff from the Solar Explorer camera. So then I'll just conclude on tungsten. It's a dense and naturally occurring element with the highest melting temperature known to mankind at 3,410 C. Used to make light bulbs that we all know it so well, medical devices, and imaging components for NASA. Because of its high melting temperature and ability to block radiation, is ideal for imaging the sun. And then some sun notes, the outside surface of the sun is cooler than the center. It's 5,000 degrees C, which is still pretty hot, while the inside is more than 15 million degrees C. There's a lot of energy. And then the NASA IRIS program will add another camera to study the sun in addition to the NASA Solar Explorer. So, and it sounds like ISRO is also going to do the same thing. So again, the sun is so important to us as mankind. And again, in terms of this talk, I thank you all for attending. Scott McCormick, Professor Scotty, is going to be next. And he's really great at answering questions. So we really want to have an interactive discussion with Scott. So if you have any questions about tungsten or the grading, I think Scotty can do a good job at answering, because he's really the specialist in high temperature materials. And we're so happy to have him along on this symposium.
Thank you, Tim. You know, I really want to say thank you to you, because my undergrad major and even my grad major all are chemistry, you know, high, absolutely, you know, core chemistry. And so today it was like going back to the class again and, you know, reading the periodic table, and then, you know, tungsten and metals one side and non-metals, and then, you know, these transitional material in between. And of course, you know, it's very, very high melting point makes it one of the most better things, and, you know, brittle at lower temperature and absolutely ductile at higher temperatures. So thank you, Tim. I think normally I would have found it very boring, but then, you know, when you come from that hardcore chemistry background, it helps. Thank you.
Well, thank you so much.
Thank you, ma'am. Thank you for stepping in. Thank you so much, Tim. That was a very, very highly interesting presentation. Thanks again for that. Ladies and gentlemen, now we request the keynote speaker of the day, Scotty, to make his very important presentation. Scott completed his bachelor's engineering with first-class honors in materials engineering at the University of Wollongong, Australia in 2013. He then completed his PhD in material science and engineering from the University of Illinois at Urbana-Champaign, USA in 2019. He is now an assistant professor of material science and engineering at the University of California, Davis. His research focuses on the interplay of crystal symmetry and energetics of materials in extreme environments for applications in space exploration. Over to you, Scotty. Thank you.
Thank you very much for the introduction. Before I get started, can everyone can hear me okay, and everyone can see on my screen that I'm sharing?
Yep.
Awesome. Thank you very much for the invitation to present. I'm looking forward to sharing 4 stories with you all about materials for planetary exploration. And so the 4 stories that I want to share with you, I've got shown here, right? So the first thing we're going to talk about is high-speed vehicles on Earth, so hypersonic vehicles on Earth. And then we're going to transition over to this idea of interplanetary missions and what are new propulsion techniques for traveling in the vast expanses of the universe. And then once we've done some traveling in this space, we're going to talk a little bit about how we design systems for re-entry into different atmospheres like Mars. And then I want to finish off talking about this idea called Imagineering. Right? And I really like this idea because it allows us to take current ideas in science and physics and then start applying them to start to imagine what the future could look like for this. And when I say the future here, I'm referring to things that are more like 100 to 200 years in the future. And we'll start to pose questions: what will future space travel look like? Okay, so let's jump into this. So the first thing that I want to chat about is hypersonic vehicles. And so first, the first question that I want to pose is how fast is fast? And I want us to think about this so we can start to get an appreciation of actually how fast a hypersonic vehicle travels. Right. So the first thing I want to bring your attention to is, these hypersonic vehicles, they travel at speeds that are faster than Mach 5. And so 1 Mach is essentially the speed of sound. And we can kind of compare that to some other things that we may be more familiar with. So if we're driving our car, down a regular highway, the speed of our car is typically around 100 kilometers per hour or 60 miles per hour. And that's only 0.08 Mach, right? So you can see that's only a fraction of the speed of sound. And when we travel in a plane, the speeds that we kind of reach here are around 0.7 Mach. So still a lot slower. We can also think of a bullet from a gun, right? When we fire a gun, this is actually where we actually break something, right? We actually reach a speed of 1.61 Mach. And when I say here that we break something, I mean that we're actually breaking the sound barrier, right? We're breaking the speed of sound and we're getting faster. But still, this is much slower than that of a hypersonic vehicle. And so you probably all heard of the Concorde, right? That was a plane that was designed that could fly at supersonic speeds, right? And it can fly at 1.76. So it's a little bit faster than, say, a bullet fired from a gun. And those of you that are interested in, say, like spy movies, you've probably heard of the Blackbird. Is this interesting jet that was made in the US a few years back. And its highest speed was 2.86 Mach. So the key point that I'm trying to make here is that this speed of Mach 5 is a lot faster than our traditional means of transportation, right? Our traditional means of travel is extremely fast. And when we start getting up to these extreme speeds, we start to encounter some extremely difficult problems that we have to overcome. So now that we've got an appreciation of how fast is fast, I want to talk about the difference between supersonic and hypersonic, right? And over here, you're probably seeing this picture before. It's a picture of a fighter jet breaking the sound barrier. And we can see this shock wave, right? This shock wave forms when we start traveling at supersonic speeds. And this shock wave actually condenses the air around it and causes water to precipitate out. And that's what this bubble here is. It's water that's precipitated out of the air from this shock wave. Right, and this occurs when we hit around Mach 1. But the core challenge when we're trying to get to Mach 5 is that this barrier, right, this wave starts to actually get compressed over the front of the vehicle. And when we get this compression over the front of the vehicle, we start to get extreme heating. Right, and I have a visual here that kind of shows this. Right, so we have our traditional subsonic flight. Right, this is an aerofoil. We have our air just passing over it. Once we hit transonic, right, that's just below Mach 1, we get this shock wave, that forms in the back. So in that image I showed before, this was visual of that water vapor that was forming in that shock wave. And as we transition to supersonic, you can see that this bow shock wave is at the front, and we get a trailing shock wave at the back. But as we increase our speed further and further, this starts to compress itself over and over our aerofoil until we get dramatic and rapid heating, right, over the top of our aerofoil. And when things start to get extremely hot like this, we can also get plasma formation in the air, right? So we're saying here that the oxygen and the nitrogen in our air starts to break down and form plasma. And so we encounter this environment that is not only extremely hot, but also extremely corrosive, right? And this is one of the core engineering challenges with designing systems to be able to withstand the environment of a hypersonic environment. Okay, so what is the fastest vehicle that's being created? This one here is the NASA Boeing X-43A, and it's basically the fastest vehicle on record, right? And it has a top speed of 9.6 Mach, right? And the key thing I want to highlight about this system that was made in the US is that it has a propulsion system, right? And that means it has a means of propelling itself. And this is going to be important when I show a couple of other vehicles. But like I said before, right, this extreme heat and this extreme corrosive environment is going to be up here at the nose of the vehicle. So there's a lot of materials design that has to go into selecting the materials for this nose tip for the system to be successful, right? And I have a picture here that's highlighting, back in 2004, some of the materials that were used in this system at the tip, right? So here's a material here that will be familiar to you, tungsten. This is what Tim spoke about. But also around the tungsten, we have some carbon-carbon side chines, right, that go around the edge of it, right? And also we also have some carbon-carbon on our control surfaces. And again, we're picking carbon-carbon as a material here because it can withstand these high temperatures, right? And then here's a picture over here of the actual system of this leading nose edge. And the key point that I want to highlight here is that the reason why this nose and these leading edges are so critical, right? As you can imagine, if something's flying at that extreme speed, at that hypersonic speed, any degradation to the nose is going to cause a change in the aerodynamic efficiency of the vehicle. And then you'll see all of a sudden a dramatic drop in the speed of the vehicle and no longer be able to fly. And so one thing that our lab is doing, right, our lab is studying different types of materials that could potentially be used as these leading edges. And some of these materials are things like zirconium diboride, zirconium carbide, and a couple of other material systems. So what are some of the other fastest vehicles that are known? So here's one that's been developed by China. You may have heard about it in the news back in 2021 in October. It was one that flew around the Earth. So it was able to circle the Earth in 5 hours. And now the key thing that I want to highlight here is, so you'll notice this is faster than the one that was developed in the US. However, it does not have a propulsion system, right? So it can't propel itself. It needs something else to propel it. And there's another vehicle over here, the Avangard, that was developed in Russia and revealed in 2018. So you may have also heard about that in the news as well. It can reach a whopping Mach 27. So that's an insane speed. But again, it has no propulsion system, so it can't propel itself. It needs another source to propel it. Okay, so I hope you enjoyed hearing some of the fastest vehicles on Earth. So now I want to transition away from Earth and start talking about some interplanetary vehicles. And specifically, I want to talk a little bit about nuclear thermal propulsion and the advantages of it. But first, when we're going to be traveling interplanetary, where are we going and why? Right. So we want to be traveling from Earth to Mars, right? And this is an extremely long way away. It's around 325 million miles. And our current method of travel is using these chemical rockets, right? And these chemical rockets can reach speeds of around 40,000 kilometers per hour, which is around Mach 32. So extremely fast, our conventional rockets. And, based on this, it's going to take around 9 months to get there and 9 months to get back. So how does our conventional rockets work? Well, we have two different types of conventional rockets. We have a liquid fuel rocket and a solid fuel rocket. And the way these rockets essentially work is that we mix two fuels together, a liquid fuel and an oxidizer. And that's the same for the solid, right? We basically mix a solid fuel and an oxidizer. And all an oxidizer is something that will burn, right, when you add oxygen to it. So basically, we're having an exothermic reaction, so something that's going to produce a lot of heat. That heat essentially heats a gas. That gas expands, and it's that expansionary effect of the hot gas that's actually going to propel our rocket forwards. So a newer concept that's being developed is that of what we call a nuclear-powered rocket. And the basic mechanics of how this nuclear-powered rocket is very, very similar to the conventional rocket. And what I mean by that is that the nuclear-powered rocket is going to be using a hydrogen gas as the propellant, right? So it's still a gas that is being heated and expanded that's going to be providing the thrust. The key difference here is that the heat is not going to be produced by a chemical reaction, right? The heat is going to be produced by a nuclear reaction, right? So you can see in here in this rocket shape, the nuclear reactor is going to be situated in here. We can zoom in. We have a pool of liquid hydrogen, and then we have some nuclear fuel rods. So these nuclear fuel rods are what's going to be producing the heat. Liquid hydrogen is going to be passed over them. The liquid hydrogen is going to be heated up from a very, very low temperature to all the way up to 2,700 degrees C. That's going to cause a massive expansion of the gas. And then that gas is going to be shot out the bottom, and that's what's going to provide the thrust, right? And it's estimated that using a nuclear rocket system, we'll be able to achieve around 5 times the speed compared to a chemical rocket, right? So we're able to get Mach 160, which is crazy fast, right? And so one of the key challenges in designing this system is actually designing the pellets, the nuclear pellets that are going to be used in this nuclear reaction, right? And currently, it's these trizo fuels that are going to be used. And essentially all this is we basically have a uranium source in the center. We have it coated in some carbon. Then we have a silicon carbide layer, and then we have an outer carbon layer, right? And essentially these balls are what are going to be participating in the nuclear reaction. And the reason why I bring these up is that one of the projects in our lab is actually studying new types of fuel kernel sources, right? So this one in this picture is just made of uranium. So we're looking at developing uranium carbide nitride fuel sources that can get to even higher temperatures. So you can essentially have the reactor operating at an even higher temperature to then get even more thrust. Right. Now, so why are people so interested in this nuclear thermal propulsion as a different source? Well, if you actually compare to all the other trips we've had to Mars, typically it's been taking around 9 months, but using a nuclear power source, we'll be able to halve the time, right? We'll be able to get the time down to around 3 to 4 months. So it's a lot faster, which means that when we're trying to get to Mars, there's a lot less exposure to galactic radiation, and it's a lot quicker if there's a problem to get there and get back. So this is why there's a big push currently for the development of this sort of nuclear thermal propulsion. Okay, so now we've talked a little bit about how we're going to get to Mars, right, from traveling from Earth. But once we get to Mars, we then have to start to consider how we're going to re-enter into the Mars's atmosphere. And there's a lot of materials challenges associated with this. And SpaceX is currently one of the core leaders that are working on coming up with the best solutions to re-enter the Martian atmosphere. So for those of you who don't know, this is the spaceship that SpaceX is proposing they're going to use. It's called Starship. Just in this picture, you can see in comparison, it's a little bit larger than the other conventional ships that have been developed. And the other key point about Starship is that it's not a nuclear-powered ship. It's a conventionally chemical-powered rocket. And so the idea is that we want to use Starship to fly from Earth to Mars and then re-enter through the atmosphere, right? And so just so everyone knows, right, so the properties of Mars are different when compared to Earth, right? Mars is actually a little bit smaller, and so it has a much lower gravity. And we can actually use this to our advantage when re-entering the atmosphere because it means that there's going to be less gravitational force. But also Mars's atmosphere is a little bit, it's less dense than Earth's atmosphere, right? And this can also be an advantage because it means we're going to have less friction heating on our surface, which is going to make re-entry a little bit easier. And so now here I have a picture just showing Perseverance. This is a NASA probe when it's coming to land on Mars's surface, right? Just so everyone can get like a general idea of the trajectory of what it looks like when an object is coming to land. And I really want to highlight this region here of the re-entry process. And this is the region here where we get maximum heating through the atmosphere. And you'll notice here we have this heat shield, right? This thermal protection system, right? So when NASA's Starship is going to be coming through the atmosphere, this is going to be one of the key reasons or key spots where failure could occur, right? So I want to talk to you a little bit about what some of the cooling systems, the thermal protection systems that SpaceX is considering to try and deal with the thermal management to get Starship to land safely, right? And currently, there's a variety of types of cooling systems. All right, so we have what we call passive and active, right? And passive typically relies mostly on conduction, convection, and radiation to remove heat. And the active system usually involves passing a fluid over the surface to help accelerate that heat transfer, right? And currently, Starship is proposing, although they're trying to develop a transpiration cooling. And so what is transpiration cooling? Transpiration cooling is essentially they're going to be flowing a fluid through the skin of the rocket, right? And this fluid is basically going to allow for heat transfer through two ways. One is going to be evaporation, and the second is through the actual heat capacity of the fluid that throws through these. And this transpiration cooling is one of the most natural ways of cooling in our universe. In fact, humans use transpiration cooling to actually cool ourselves down when we're exercising. So you would have noticed when you run, you get hot and you start to sweat, right? So it's the exact same process that SpaceX is proposing to cool down the Starship, right? Because when we sweat, we sweat out water. This water evaporates and is also transported from our surface, and that's what helps us cool down. The key difference with SpaceX is that they're probably not going to be using water. They're probably going to choose a different type of liquid gas to try and maximize that heat transfer. And they're undecided on what they're going to pick yet, but they're definitely looking into what the best options are. And so the idea is that once we have our thermal protection system sorted, we can safely land on Mars, and then we'll be able to start building our civilization on Mars. Okay, so we've talked about three different stories here. We started off talking about, what are the fastest vehicles on Earth. Then we started talking about the nuclear thermal propulsion to get us from Earth to other planets. And now we started talking about re-entering into the Martian surface and starting to set up a civilization, or starting to set up infrastructure on another planet. So now I want to shift gears a little bit and start thinking about this idea of Imagineering. Right. And I really enjoy thinking about this idea of Imagineering, because I really think it's how some of the best discoveries in the world come about. And like I kind of highlighted before, the way this Imagineering works is kind of where we take basic concepts from physics, chemistry, and engineering, and we start to project them into the future to start to get an idea of where we think we'll be in the next, say, 100 or 200 years. And so when we do this exercise, I want to pose a problem for everyone to just kind of think about for a minute here. And this problem that I want you to think about is that, here I have a picture of the United States, and I have this statement here saying that in the 1800s, if I wanted to travel from New York all the way over to San Francisco, it would have taken me around 4 to 5 months, right? So it's a very long time. In fact, that time scale is on the order of us going to, Earth to Mars right now, right? Now, obviously, if you've been to the US, you'll notice that if you actually want to do this journey, right now in 2022, this journey can be achieved in 43 hours, right? So that's around 0.05 months. So the question that I pose here is, what's changed, right? What's enabled us to dramatically reduce this travel time? Right. And so if we think about this, the key answer to this question is infrastructure, right? What we've developed to make us travel further is we've developed a series of roads. We've developed a series of airports, a series of infrastructure that's dramatically reduced our travel time. So the question I pose here is, what will infrastructure in space look like? And how will we be able to travel interplanetary in the next 100 years? And what's really cool is that a lot of scientists and engineers have been thinking about this for a long time, and they think they've come up with quite a unique solution. And this solution is what they call tethers, right? And this tether is a pretty simple concept, right? Basically, all a tether is a weight with a latch at the end. And just so everyone knows, this base technology of these tethers already exist. In fact, different space organizations have already tested out this tether concept. And the way this works is that we have our weight with our tether. It rotates, right? You can see it here rotating, it's rotating. The idea is that when we're on Earth, we'll have an object like a rocket come up, it will get caught by the tether. And as this tether is rotating, the tether will then fling it off into space, right? And the idea is that because the tether is rotating, the object that attaches down here will get more momentum and be able to be flung up higher. And this basic concept has already been demonstrated in Earth's orbit, and it's already been used to toss things into higher orbit. So the core thing I want us to think about here is, what if we could extend this further? Right, so it's already been demonstrated that we can increase the orbital height by using this tether concept. But I want you to think about what if we could use this to catch an object from Earth and then fling it out further into space? Right, so we could develop this tether system in Earth's orbit to fling things further out to space. And if we already have, say, some infrastructure on say Mars for us to live there, what if we could also develop a tether on Mars as well, right? And the general concept here is that, you know, we could fling objects from Earth using this tether system to Mars, catch them with another tether system to bring them back down onto the Martian surface. But then we could also use the same tether system to also fling them away, right? And this kind of concept is a very, very interesting concept. And if you want to learn more about it, I highly recommend you go on YouTube and Google the Skyhook by Kurgazarts. They have an excellent video that goes through the sort of basic engineering and science behind this concept. But some of the key things about this, the key things I want to highlight is that using a concept like this, it's predicted that travel time to Mars can be reduced to 3 to 4 months, right? Which is incredible, right? Because as of now, using conventional rockets, we're up around 9 months. So this would bring it down to be on par with traveling with, say, like a nuclear propelled system. But even more amazingly is that using something like this, we could actually reduce spacecraft sizes by around 84 to 94%, which is insane, right? That means that using this sort of system, we wouldn't have to lug around all the fuel for our ships, right? We could use this momentum transfer to really just fling things around our universe, around our solar system. And this would mean that we could start designing rockets, we could start designing spacecraft to more reflect the sort of amenities to make it, you know, more pleasant for human travel. And so the kind of, 100 to 200 year goal would be use this concept of tethers to start to set up a near zero propellant transport network within the solar system, where you could imagine you could fling things to Mars, use Mars as a hub to fling things over to, say, the asteroid belts to do some mining, and then fling ores back to, say, Mars for construction projects, or even fling things over to other planets in the solar system to also act as construction projects. And I see that this sort of system would actually enable us to successfully, navigate our solar system in the next, say, 100 to 200 years. And I think this sort of idea of thinking about this is extremely exciting. Okay, so with that, I hope you guys all enjoyed this. Please let me know if you have any questions. And just as a summary, what we kind of talked about is we talked about some of the fastest objects on Earth and some of the material challenges associated with designing them. We also talked about the sort of next generation propulsion systems that will be developed in the next 5 to 10 years. And then we also discussed thermal protection systems for entry into Mars that will also be developed in the next 5 to 10 years. And so these 3 areas were really things for the next 5 to 10 years. And then we took a step away and started thinking about what will the future look like? And when we said future here, we're referring to what would things look like in the next 100 to 200 years. So if there's any questions, feel free to ask. And I thank you all for listening.
Scotty, I have a question. Can you hear me, Scotty?
I can hear you.
Yes, in the movie The Martian, they use a solar ion engine as the main way they get from the Earth to Mars. How, in terms of speed-wise, how does that compare with the nuclear propulsion, like say a solar ion engine?
Yeah, so from my understanding, it can't get anywhere near as high thrust. So the momentum is limited by the number of molecules that you can fly out the back.
Mm-hmm.
And from my understanding, with that system, they can get the molecules to fly out extremely fast, but there's a limit to the number of molecules they can shoot out, right? So the overall momentum doesn't match that of like shooting out a whole bunch of hydrogen. So it's really in the nuclear thermal propulsion system, it's really the large amount of hydrogen that you're shooting out the back that's giving you so much extra momentum.
And then braking, I think the issue in The Martian, I don't know if people, it's a great movie to watch actually, because there's a lot of cool, but the braking of the ion engine is a big problem because as they get to high speeds, it takes a long time to slow down. So is that, the SpaceX, are they considering with this nuclear engine, it's also the ability to slow down so you don't hit the planet too fast?
No, you're exactly right. So when I quoted those max speeds, right, they are not the speed that we traveling the whole time, right? Because there has to be a speed management to brake once you get there, right? And this is why I honestly think the tether concept is so brilliant, because just as you can fling something away from the Earth or away from the planet, when you catch something, you can also reduce its momentum that way, right? So the tether system is actually brilliant for braking and accelerating. Any other questions?
Yeah, I think everybody, if you want to ask a question, it's a great opportunity to kind of help clarify some things. I saw there was one question from somebody who was asking about how is it possible to reduce the travel time, and that's why I asked about alternative propulsion systems. Again, if anyone has any questions, it'd be great. We can help.
Scott, would you like to answer that? There is a question that we received by WhatsApp from an engineering student who would like to know how is it possible to reduce the travel time to Mars?
Yeah, so it's really increasing that specific impulse, right? And so that's one of the key things that the nuclear thermal propulsion provides over conventional rockets. And even the same as the ion engine, right? The ion engine is still an excellent system that will always be used in space because it can provide a constant thrust, right? And I think the ion engine's core role is going to be for like slight maneuvering, right? Stuff like that. But I think this nuclear thermal propulsion is going to be our initial way of like getting somewhere so that then we can start to develop infrastructure. And then once the infrastructure is in place, we'll probably be using less thermal nuclear propulsion and more relying on other steps like the tether concept, right, to maneuver around. But I think the first time going somewhere, I think NTP, the nuclear thermal propulsion, will probably be the first step.
Okay. Thank you. Thanks for that. Any other questions? Nikki, any questions from your side? I think there is some question now that has cropped up. Nuclear detonation engines and its future impact in space sector. Tim or Scott, would you like to take that?
I think it's Scott would be, because I don't think it's a nuclear detonation engine, but maybe Scott can talk more about that drive, that nuclear drive.
Yeah, so I can make a comment on the detonation engine. So the detonation engine concept, I would say it's still very much in the concept stage. It's very difficult to have because the idea behind it, right, is that you basically have a bunch of nuclear explosions behind you that's going to shoot you forwards. The problem with any sort of travel is that explosions are hard to control. So we usually like to avoid explosions, right? So that concept, I say, is still very, very early on. And currently, what I know the United States is focusing on is definitely this nuclear thermal propulsion systems, where they're basically using a nuclear reaction to provide heat to expand the hydrogen gas. So maybe in the next 50 years, maybe we'll get better at controlling small nuclear explosions to like try and use that. But I think as of now, that's not something that people are exploring as much. So I think the next question here is at such high speeds, how are astronauts protected from blackouts due to the high Mach speeds? So in answer to that question, it's actually the acceleration that knocks someone out. So it's not necessarily the speed. So the trick there is you have to accelerate someone at a rate that is low enough so that they don't black out. So don't quote me on this, but I think it's around like G6 or G6 to G9, I think is the point where people start to pass out. And so when I say G there, that's 9.8 meters per second, right? So that's—
And Scott, a friend of mine who was an F4 Phantom pilot in Vietnam, and they use pressure suits. It's kind of the spacesuit, the more advanced spacesuits, I guess, pressurizing can help you withstand the Gs. But again, I think there's practical limit of about 6 Gs. But again, but spacesuit technology has, especially with SpaceX's new suits, they are engineered to help keep you in one spot. You don't want your body to flow like a liquid. So I think there's a lot of some spacesuit development is real key to that.
Yeah.
Interestingly, Scotty, that's a question from our friend in Uganda. We have participants from Uganda. So that's a question from our friend in Uganda.
So we have another question here. When gravity in Mars or any other planet is very low, how do we manage to launch probes on their surface? Yes, that's a very good question. So when you have lower gravity, that's actually better, right? Because it means you need less energy to remove it from the surface. So in places like Mars, there's actually ideas of people being able to use like, there's concepts where people think they'll be able to use like rail guns to like launch things off Mars's surface. And that's something that we can't really do on Earth because we have so much more gravity. But we might be able to, once we get infrastructure on Mars, we might be able to set up, rail guns to shoot things into the atmosphere and then have them kind of, reach the escape velocities that way. And if you're interested in that, there's a really good YouTube video that talks about mining of mercury, where people want to use rail guns to propel ores off of mercury, which is kind of really fun and really cool. Any other questions, thoughts, or concerns?
Nikki, do we have any questions from that side?
I currently don't see any questions right now.
Financial or security risk. That's why I never worried about it. But if Greg or them or
Can we request for remarks from Madam Mamta Rani? Madam Mamta Rani, your remarks, please.
Oh, it has really been a wonderful learning from each one of you, from Tim, from Scotty, and from you. And I hardly knew anything. So, knowing a little more about unknown, and absolutely, space has always been one of the most curious things for all of us to know. So I think it has been a wonderful session, and I would request that we should encourage more and more students to take aerospace engineering. We should actually encourage more and more students to undertake metallurgy, because it and fundamental sciences, and that convergence of all fundamental sciences, that is transdisciplinary, interdisciplinary, and multidisciplinary education, where all the subjects and their specific knowledge converge to actually create and develop a very useful product. Thank you so much. Thank you.
Thank you. Thank you, Madam. Scotty and Tim, there is another question. Would you like to take that? How are tungsten optically made as films and telescopes for solar viewing applications?
I can say that tungsten is actually a grating is a optical structure that consists of a lot of like slots or lines. And because tungsten it absorbs radiation, you can actually diffract sunlight. And a lot of the radiation that's produced by the sun, it's not a lens in the particular sense of a normal lens, like a optically lens, and it's not optically clear. Maybe thin layers of tungsten, about less than a micron, might be optically clear. But again, these are advanced imaging systems, kind of like what's used in an X-ray machine to detect an image. It's not a traditional image. They are electron imaging devices. Optically, some materials may exist. We have worked with Elcon with development of high temperature optics using ceramics. So there are new ceramic systems that are combined minerals that can be used as optical devices into the range of around 2000 centigrade. I think sapphire melts around 1800, 1900 C. So this, but again, it would need some cooling. So there is some research on that, and part of it was done by UC Davis, by the way, on the optically transparent hypersonic materials by Dr. Mia Mukherjee. It was done with that, and I think Dr. Subhash Rusbud has maintained some of the research, and he's another ceramist at UC Davis. Again, I can't talk. I highly recommend looking at UC Davis, the engineering and the kind of the work done there. Scotty is really taking them to a new level in understanding of high temperature materials, and there's always a quest for more high temperature transparent materials to be developed. And it's, again, one of the many challenges that we face as we try to image the sun or other sort of hot objects, or also be able to see something when you're in a hypersonic plasma.
May I ask a question, Tim? May I ask you a question? Why is tungsten used as surgical cutter? Because you were saying that, while for knee replacement and all others, tungsten is used as a surgical cutter. So what actually makes it different from all other metals that it is used as a surgical cutter?
It's a very stiff material, and so the doctor, and it goes on the end of a 3 millimeter diameter syringe. It's like a tool. And they place it in there, and we put a gold coating on it, so it's electrically conductive. And then they actually can heat this very hot. It's a very hot, and it doesn't deform while it heats, so it's very stable. So what's hot to tungsten, it may heat up to a 300 C or some, just enough to cut the tissue. So it's a hot cut. It's like it's cutting and using heat, but it doesn't deform or melt or bend, and it doesn't contaminate. So tungsten, because it has a low vapor pressure and also is a very stable material, doesn't hurt the body. So that's why it's chosen for the in situ cutter like that, is it can be made small, stiff, be able to be heated reliably and not bend or deform, so the doctor can make very precision insertion. It cuts, and they usually have like some optics in there. So there'll be like a camera that's also inserted. So if you have knee surgery, there's no like 3 or 4 different holes that they put in your knee, very small. And so they could watch this cutter occurring. And the recovery times are very, very rapid now. If a good friend of mine had knee surgery and was recovered within about 3 weeks, and they don't have to open up the whole knee anymore. It's just marvelous how these small cutters made out of tungsten, how they enable fast recovery time, because they don't have to make such big cuts. So that's again one of the advantages of the material. It's an unusual application.
Thank you so much. Thank you.
Thank you, Tim. Ladies and gentlemen, with that, we come to the close of this 5th edition of this webinar series. We encourage the participants and also the registered delegates to send in your questions. We will, along with Nikki, we will send the questions to the panelists and request their answers. We would like to convey our special thanks to Madam Mamta Rani Agarwal, a very high-ranking official from the Ministry of Education, Government of India. Thank you so much, ma'am, for your presence today. It has been a great source of encouragement. And as is always, thanks to Tim's leadership, and a special thanks to Scotty for all your energy and all for the new way in which you present things. We look forward for your visit to India sometime very soon. And India welcomes Scotty, and as always, India welcomes Tim. Thank you so much, all the participants. Thank you so much for the panelists. And again, a very, very good morning to US, and good evening and good night to friends in India. Thank you again.
Thank you.
Thank you, ma'am. Thank you so much.
All right.
Thank you, Nikki.
Thanks, Stevie. Thanks,
Thank you.
everyone, for joining. Bye.
Thank you. Thank you.